Hello, my name is Dylan Hacker, and today we will be solving and coding a network of pipes. We'll be determining the flow in each of the pipes, and what the system looks like is right here. You can see 5 nodes labeled from 0 to 4. 0 and 4 are both external nodes, as 1, 2, and 3 are internal. We know the pressures at the external nodes. 0 is 200 pascals, and then at node 4 it's 0 pascals. We know that the altitude at node 0 is 30 meters, and the rest of the nodes' altitudes are 0 meters. You can see 6 pipes in there. We'll be calculating the flow in each of these pipes. As you can see, we have labeled right here the pipes. One pipe is from 0 to 1, and then so on, with the length and the K value. The length of pipe and K value will both be used in this Bernoulli's equation down here, which will help us find the delta head, which will in turn help us find the flow later on in our code. We do know that the pipe diameters in each of the pipes is 0.1 meters, and the pipe roughness is 0.001 meters. This Bernoulli's equation right here is the delta head, which is this first part right here, plus this, which includes the friction factor. And for the friction factor, we are using the Churchill correlation. And we can find the delta head by moving this equation over to the right-hand side, setting them equal to each other, and we'll be able to find that. We know that the velocity is going to be 4 times q, which q is the flow, over pi d squared, because this comes from the q equals VA, which is velocity times area, and we know that the cross-sectional area of the pipe is a circle. So that's nice and simple. This velocity is derived from this equation up here. Some simple algebra moving this over. That's negative delta H now, which is delta head. And then the square root over this. Perfect. And then Q is Q times velocity times area. Nice and simple. So now that we have outlined the problem, we can go ahead and start our coding. First thing we have to do in coding is always import a NumPy library, numerical Python. And I like to do it as NP, keep it nice and simple. Shift enter that, make sure it registers. And the next thing we're going to do is set some basic variables, initialize some variables that we'll be using. Gravity, we'll be using Reynolds number, which is rho dV over mu. We'll be using that in the friction factor, so we want to go ahead and get rho and mu initialized right away. Pipe roughness, diameters, all that stuff. So first one is gravity, which is 9.81. We're going to do rho, which is going to be equal to 1e to the 3, 1 times 10 to the third. Mu is going to be 1e to the negative 3. We're going to do diameter, which is equal to 0.1, like we said, and then ED, which is equal to 1e to the negative 3. Now that we have that initialized right there, looking at this, our first function that we want to create is going to be for the friction factor, the Churchill correlation, and that's at the bottom right there. You can see all of this stuff. We'll be plugging it in. So define f, which is going to what we're going to be calling the function, with the initial the parameters of the Reynolds number and ED, which is the roughness of the pipe. We're going to be having an A, like we said, A, B, and then what it's going to return is this equation right there. And A is going to be, oh, I didn't mean to do that. A is equal to all this in parentheses, 2.457. times, this is why we import NumPy right here, log, and then it's 1 over parentheses, big parentheses, 7 over Reynolds number, that value times 0.9, not times, to the power of 0.9, right there, and then it's going to be plus 0.27 times ED, which is the roughness of the pipe. That looks good. Let's see, where's that hookup? Right there. And that is right there. And that is all to the power of 16. Now for our b value, much simpler than that, it is going to be 37530, 37530, 37530 over Reynolds number. And this is actually going to be to the power of 16 as well. And then we're going to have a return of 2 times, and then parentheses 8 over Reynolds number. This is going to the power of 16, or to the power of 12. And plus 1 divided by parenthesis a plus b. This is going to the power of 1.5, and then the whole equation outside of the 2 is going to be to the power of 1 over 12. Shift enter that, and let's go ahead and test our function to see if it works appropriately, and we're going to be doing that right there. And that does not look right at all. So we have to go figure out what we did wrong. It's gotta be something. I'm assuming it is right here. Power of 16. 2.457 times 1 over. Let's see how these parentheses match up. Matches up nicely. 8 over Reynolds number. Let's make sure that's where it's wrong. No, it seems right. Huh. I know our value should be much smaller than that. 37530 over Reynolds number. That's correct. 0.9. Let's just put everything in parentheses just to make sure. .27 times ED, which is correct. Let's put this in parentheses. Let's put this. Invalid syntax. I have one too many parentheses, maybe? One too many? Is still not correct. What are we doing incorrectly? Let's just redo this whole bottom part right here. Just type it again. Sometimes that is the best option. So we're going to do 2 times 8 over Reynolds number. And this is to the 12th power. That is plus 1 over A plus B. .5 power right there, and then that right there to the 1 over 12. That is the issue right there. I wasn't doing it in parentheses, correct? Boom, bada bing. You always have to make sure your exponents are in parentheses, because if not, then it leaves you a lost cause. So once we have that number is correct. We know that it is correct because it's in between 0.002 and like 0.25, right around there. That's what all of the friction factors should be equal to. So now that we have that out of the way, we want to go ahead and define delta H, our delta head, and our inputs for this is going to be Q, L, K, D, and ED. And what our delta head is going to be equal to, well, first we're going to have to, it's going to be equal to this equation right here. This right's part of the equation right there. First, we're going to have to define our velocity, because the velocity is in that equation. And what that is going to be equal to is right there, 4 times q over this, in parentheses, numpy.pi times diameter squared. Now, using that, we can find our Reynolds number, which is rho times d times v over mu, and these mu and the rho and the d are all coming from these variables that we established up above. So once we have that, we want to go ahead and return negative parentheses k plus 4 times the frictional factor, which we're going to be using the function that we created earlier, RE over ED, times L over D, length over diameter, and this, I like to put another parenthesis right there, times, this is going to be velocity squared over 2 times g, lowercase g, and I am forgetting a parentheses right there, and then we can go ahead and test our function to see if it's working appropriately. Length of 3, I don't know, k value 1.5, and then d and ed we both established from above, and we get ed is not defined because I did not capitalize the d right there, and it gives us a gigantic negative number, which it makes sense that it's negative because the delta head is positive, and with a positive delta head we're going to have to get a negative because the flow should be coming negative if the delta head's positive, because final minus initial gives us a positive number, so we know that the flow would have to be negative there. But we want the flow to be positive maybe, and we want that means we want a negative delta head, and what does that give us? Bad. So we get this j in here as well. We get negative, we get all this wacky stuff, right? Well, we don't want that. So what is our problem here? Our problem is that our Reynolds number can never be negative. We can never have a negative Reynolds number. That is bad. So what we're going to have to do is make this an absolute value. Absolute value of that right there. That'll give us a positive v. But what we're going to have to do is multiply this by the sine of q, because we do want the correct sign out of this equation. So we get that. Boom! There it is. That value is going to match this minus the sign. So the negative, perfect, they match up perfectly. That is exactly what we're looking for. So now that we have delta head, what we're going to want to create next is a flow function. Since we can get the delta head, we want to get a def flow, which is going to input basically the same stuff, except for this time, instead, it's going to be a dh. And what it's going to do is it's going to return a result flow. All right, so what are we going to have to put into that? So we're going to be using the Newton function. So we're going to, let's import Newton right here. We want from SciPy optimize dot optimize imports, and what we're going to be importing is Newton. And what Newton does, it takes in a function and an initial guess, and it drives that to 0. Drives the function to 0. So we want a new function now. Let's shift enter this. So our new function now is going to be f to 0. And this is going to take in a flow rate And what we're going to do is we're just going to copy this right here. Although we don't want, let's see, perfect. Although we don't, I didn't mean to shift enter yet. Okay, and that is not matching up. What? Why is it tabbing now? Sure, that works. Okay, and what it is going to return is some delta. We're going to do a negative delta head plus this value right here. You can go ahead and copy and paste this. So given the delta head and all this stuff is indeed known, it will be able to solve for us. So let's see. Let's define a delta head equals, I don't know, 40. We'll get a k value of 1.5. Length equal to 1.5 as well, or 3. We'll make it equal to 3. And then we can do our f(0) function given q, given some flow rate, I don't know, 50. That's really high. Let's go like 0.1. And it'll give us some number, correct? Now, what we're going to do is, okay, it works. That's all that we were checking there to make sure that there's no bugs with it. So now that we have this right here, we know that we're going to have to plug this into here. Tab all this stuff over. We can get rid of this now. And you see how this is just putting out this exact thing right here. We can go ahead and use that function up there. So we can go dhead, and then just copy this, paste that right there. And we want an absolute value for this delta head so we don't get anything confused. Dhabs is going to be equal to np dot absolute value of dh. Alrighty, and now what we're going to need in order to use our Newton function is we're going to need a QGuess. And for our QGuess, we're going to be using numpy.pi times d squared over 4, the area, and this is going to be times our velocity, which we found right here, which is negative delta h. So we're going to use the square root. And this is where the dhabs comes in place, because you can't have a negative under square root. That does not make any sense at all, right? So what we're going to do is dhabs over, and then big parenthesis, it's going to be k plus 4 L over d. So I want to go ahead and copy and paste this right here. Although we're not going to be using our correlation, our Church-Short correlation this time, we're going to actually be putting in our own guess here to see what we get. And 0.01 is right in the middle of the 0.002 and 0.25, like I said earlier, which is what all the friction is going to be, all the friction factors are going to be in between. So once we have this, we need to make sure everything lines up perfectly, and we have to multiply this by 2 times g. And that should be a 2, not an add symbol. We can shift enter that, and dhabs is not indented, and neither is QGuess. So it is going to be mad at me for that. And what we're going to do down here is we're actually going to be using our Newton function. So we'll get result flow is going to be equal to this Newton function, which we imported, and the function is going to be f to 0. and our initial guess, which we just found. And we don't need this stuff in here anymore because that's what our delta head actually does up here. And if we get that, it is not indented. So now we can go ahead and test to see what is actually happening here. So we'll do flow 40, 3, 1.5, and then D and ED. See if it works. And there we go. We have a flow. But we want to check our guess to see how close our guess actually was. Let's do negative. Let's see if it works with a negative first. It does not. So it's going to put out. So what we have to do here, that's because of our absolute value. So we're going to have to multiply this by MP dot sine of DH. There we go. And once we get that right there, we want to go ahead and see what our Q guess would have been. So let's plug everything in here. We have D, we don't have D halves, we'll plug that in. What do we say? It was 40. We have D, we don't have length. Let's go, what did I say? 3, and then 1.5 for K value. See how close our guess really is. And it's pretty close. Honestly, it's pretty close. Look at that. It's within 0.02. And what the Newton does is just cycles. It finds the number that drives it to 0. Drives because we want delta head, those two, to equal 0. So now that we have that gone out of the way, we want to create a case for the very, very, very small values. So if DH is less than 0, or D halves, I guess, because we want it to be positive. It's like, I don't know, 1e to the negative 10, we'll say. We're just going to we'll just return 0.0. That just makes it so that the very, very small numbers don't end in iterations to where it won't be able to define. And I don't have a valid syntax here because I forgot a colon. So now if we test this, so if we go flow, I don't know, let's do 1e to the negative 11, and then we'll just do 1 for everything else because it does not matter. It's going to return 0 for us, which is exactly what we want. So now that we have these functions, we can start creating an array for our pipes, which I'm going to go ahead and do off screen because it's going to take a minute, and I'll be back in just a moment. And we're back. Alrighty, as you guys can see, I went ahead and put in an array for all the pipes that we did over here. All of this right here I just put into an array from node to node LK, exactly like we had it on the paper. Already, and now I want to be able to create some more arrays, height, pressure, external pressure, external nodes, all that good stuff. We want to be able to define that right away. And what we're going to do is we're going to do altitude first, so Z. This is going to be an array. It's going to be 30, like we said, and then the rest are just going to be 0 values. Because that first node, the node labeled 0, is at 30 meters high, while the rest are at 0. Next, we're going to want to determine our external nodes. Which one are those? It's going to be the index of 0 and 4. Next, we're going to do external pressures, which is going to be equal to 2e to the 5th, and then 0. So the node 0 is 200,000 pascals, and then node 4 is 0, because those are both of our externals. Next, we're going to want to create an array for all the from nodes. So we'll do from nodes is going to be equal to pipes. We'll use this cool command right here, which just cycles through and it takes the index, which we declare right here, index of 0, and it's going to put all of those in right there. And we also want to set this as type int32, which is basically giving int32 is a super large number of integers, so that if you want to add any amount of pipes, you are able to. And let's go ahead and clarify that just to make sure we know it works. So 001123, exactly as we specified up here. So 2 nodes is going to work the same way. We're going to want to copy and paste this. We're also going to want to create a list of values for else, which is going to do the same thing, except for this time we don't want to declare as an int32. Because it is, we want to change that to the index of 1, because it is a decimal and we want to keep it that way. So the same thing for the k values as well. We want to go ahead and do that. That's the index of 3. Alrighty, once we have that, we want to determine the number of pipes. So we'll do n pipes is going to be equal to, and we want the number of rows. So in order to get that, we do pipes.shape, and then the index of that is 0. If we do pipes.shape down here, I'll show you exactly what it does. That does 6 and 4 rows, columns. 6 rows, 4 columns. We want the number of rows, so we choose that index of 0, which is 6. Once we have that, we want to create a list of values for our diameters. So we'll do d pipes is going to be equal to, we have to make this an array. We'll make this np full, and we want the shape, which is going to be in pipes, and we want the value, which is going to be d, which we specified all the way up here. Next, we're going to do the same thing for ed, the roughness of the pipes. So the same thing, shape is 6 from the in pipes, although it varies if you have more pipes, and then ed. Next thing we want to do is say the number of nodes. So how we're going to get the number of nodes, we know that it's 5, but what we if we add more pipes, we might not know. We want to specify according to our list, right? So if we look at this second column right here, we know that the second column will always be greater than the first column because it's from node to to node, and we determine that the from node has to be lower than the to node. So we're going to look at this right here. We're going to look at the second column right there. We're going to take the maximum number, and then we're going to add it by 1 because we start our node at 0. So n nodes is going to be equal to np.max of, we'll do pipes, this colon, and then what index we're looking at? We're looking at index of 1. And now if we shift enter that, it is, let's see, we made a mistake right here because I forgot an E. And I need a capital P, and I need another capital P. And then we have that. And look at, if we go to n nodes right here, it's going to give us 4, which is correct right there. We see 4 twice actually, but it's just taking max. And what did we say? We wanted 5, right? So we're going to have to add 1. But first, you saw the decimal in there. We want to change that. So we want to do as type int32 to keep it a decimal. And then we're going to add 1 to this value. Add 1. All right, now we are going to want to get a list of heads, right? And we can find the head at both of the external nodes because we have the pressure and the altitude. So we want to create an array of this. We're going to do np full. We're going to do n nodes and we want it all to be 0. And the best way to do that is instead of doing full, we just do zeros. And now we want to determine the heads at the external nodes. It's going to be equal to the external pressure divided by rho divided by G plus Z of those, the altitude of those external nodes. So once we have that, we can go ahead and type heads to see what our values are. Obviously, all of these are going to be 0 because the pressure at node 4 is 0, as well as the altitude. But you see this is 50, which is the only one that was supposed to change. And we haven't touched the internal nodes yet. So we will be doing that in just a little bit. We're also going to be needing the indexes of the internal nodes, which we can find now. This is going to be equal to a list of range of set of, we want pipes minus the external nodes. And see if this works correctly for us. Unexpected, that means I'm missing a parenthesis. NumPD array, list range set. Pipes. Oh. We want the speed and nodes, I apologize. That makes so much more sense, right? We cannot do in NumPy that instance is not iterable. Oh, maybe we do. When it said the list, maybe if I take this away and take this away. No. Oh, we want one. Yeah, wait, and then there's an extra one. Let me figure out why this is not working really quickly. Let's type this all out again. So we want a list, and we want, let's do set and then range. I think that's what I had wrong. Here, range, and then we want this to be end nodes. Minus set of external nodes. Okay. No, I had it right before. Oh, wait. Let's Control Z that. There we go. That is what I wanted. Okay. Let's check that now. Internal 1, 2, and 3. Okay, that's what it is. So I'm mixing up the set and the range. I put them inversely, and that was the incorrect way to do it, but I have fixed it, and there we go. So now that we have that, so now what we are going to do is we're going to do a function to calc flow. And what this is going to be giving is a head. Let's see if that's correct. So we want to create flow. It's going to be returning flow, but we're going to do flow as MP zeros and this is of pipes. And then we're going to be using our delta head function right here. So this is actually probably Q. I don't know. I'll figure that out in just a moment. It'll all make sense here in a minute. So we're going to be calculating the flow using that uses that. Perfect. Okay. So what we're going to do is I'm pretty sure it's head. Okay. We're going to be doing that. That will create a full list of zeros for the number of pipes we have. For I in range, we're going to be doing n pipes. This, and then we're going to be calculating a delta head. Oh, okay. I see. We're going to be putting in pipes or some list of pipes. Yeah. Okay, and then we're going to be doing subtraction here. We're going to do from or to node minus the head of from node because it's final minus initial. This has to be brackets. So that works right there, and then we get our delta head, and now we can use our flow of I, which is the index, is going to be equal to, we'll do our flow command. I like to make this flows actually because that is a little bit different. It's different enough. We could put our delta head it's going to be of the heads. So it's going to access these two. So from the heads. And then L of I, K of I, index I, D of I, and then ED. Although this is not correct yet because we did not specify. We want this to be the pipes. ED pipes. So once we have that right there, we want to go ahead and return our flows. See if that works out. And then if we want to do a quick check of calc flow, it's not going to mean much, but it'll help us at least to see what's wrong with our NumPy has no attribute zeros. Okay, so see, and it worked. That is exactly what we're looking for. We want that. Now try to calculate it, and now it gives us some flows, although we don't have the internal ones yet because we haven't gone that far. So that works as intended. And let's change this different. Let's make it different from our actual one. Okay, let's scrap that. And the next thing we are going to want to do is calculating the net flow. Net Q. And what this is going to be inputting is flow. And this is going to be net Q is going to be an array full of zeros again of n pipes. And we're going to be using a cool feature from NumPy where it's called @add. add at, and what that does is it takes what we're trying to add and adds it to this specific index of netq. In this example, netq, it'll be adding the flows of each pipe. So 1 to 2, 2 to 3, it'll be taking the positive and negative of those. We'll set up two different ats so that it can do the combo of the leaving and the entering. So we'll do np.add at command, and the first one is going to be netq. Next is going to be, we'll go to node, and then we'll do flow. And then it's the same thing. But this time we're going to be using the negative flow because it's from, I think. And then this is just returning netq. Alrighty, so next, now that we have the calculated netq, we're going to want to go ahead and do a netq of the internal nodes, because we know that the internal nodes all must be equal to 0. The flows must be equal to 0, because what goes in must come out. And so we'll do netq of internal, given internal pressures, because we know that all of these have to be 0. We're going to use the root function for Newton, which I have imported. We're going to be using that to be able to get the root to where we can then find the internal pressures of each of the nodes. So once we have that, we're going to want to do the head. Let's see. The heads of the internal nodes is going to be equal to the internal P divided by rho divided by G plus Z of the internal nodes. Because that's what heads is equal, as we remember on our sheet of paper that we laid out. And what this is going to return, is going to return calc netq right here, given the calc flow of heads. And this is going to be of the internal nodes. Let's see if that function runs, and it does. So now we can go ahead and move on to where we actually use this root function from SciPy Optimize. We'll be using that. It's going to, in order to use that, we're going to be needing an internal P guess. So we need an internal P guess, but in order to find our internal P guess, we're going to first need to do an internal head guess. And what this is going to be equal to, it's going to be equal to the mean of the heads of the external nodes. So this is going to be equal to, if we look back at our OneDrive, our copy right here, we can see that we want just the pressure, so we just want this part. So it is going to be our internal head guess minus our delta, or our Z of the internal nodes, and this is going to be times rho G. internal head guess is not defined because I used a lowercase g. And I don't want this, I want this to be in parentheses. Don't know why I did it this way. This is parentheses, not brackets. And I did another bracket right there. Oh my goodness. All right, let's see what our internal p guess is. And we have all of our guesses, and you can see they're all the same because the guess is what it accounts for. So now we can go ahead and use this root function. And the function that we're going to be doing is the net q internal. Let's tab that. And what is our initial guess? Our internal p guess that we just found. And it says add at. Okay. Oh. Why did it not pick up on that originally? And there we go. Here's our actual pressures that we got for our internal nodes. So we can go ahead and set this root.x to that, and it'll just, I apologize. We have to set this to result. And then we do res.x, result.x. Will just give us that list of values right there. And now we can go ahead and plug in calculating flow. We'll do calculated flow is equal to calc flow of heads. Let's see what that gives us. Boom, and there's our flows. There's our flows for each of the pipes right there. 0.618, all those. This is pipe 1, pipe 2, pipe 3, pipe 4, pipe 5, pipe 6. So now we might want to calculate the net flow for each, or for all of it, for each pipe, I should say. And then we do calc net q, and then calc flow, and then heads. And then we can go ahead and print this, calculated net q. And there it is. There we have it. We have all of ours, 1, 2, 3, 4, and 5. Although this, it should be nodes, I believe. That's where that messed up. That's why there's an extra one right there. And there we go. It immediately took out that last erroneous variable right there, erroneous element. And we have, look, what goes in must come out. We expected a negative flow from the first node because it is the start of the node and it can only push out. There's nothing coming in. It is the start of the flow. And you can see these middle ones right here. They all will add up to equal 0. So there it is. Thank you guys so much for watching. I hope you guys have a fantastic rest of your day.